so 30
okay.
So it should work. You know?
Yeah.
Oh, longest trip ever.
Turkish Airlines?
Yeah, one. I'll take it's just one. I didn't stop anywhere in Europe.
Lucky. My shortest flight is usually 22 hours.
Because you're still
in
by
between.
somewhere else. I guess that after 2 hours I should get up and do something. I don't like it.
So you won't go to conferences when it's far away, right?
It depends. You're not telling me Australia or Oceania, right?
No, I mean Eric will go. You cannot go.
It depends what you're serving in the flight, you know. The end of the economy class, crying babies with me.
Yeah, that's accurate. All right, so. Fine, we can start. Okay. So.
A question about.
Yeah, it was a project. Yeah, go ahead.
What value should we use for rho? Just standard 1,000?
For rho, just use one.
Just use one?
Yeah, so yeah, the rho. Did I not give you a new?
Yeah, we got a new.
You have another view of the rho. Yeah, just use one.
Okay.
Okay, that brings up an important point. So sometimes people come to me and ask, all right, this is a simulation. The length is given to be 1 unit. Velocity is 5 units per second. What does this mean? How many millimeters? How many meters? So in simulations, you don't care because everything is non-dimensionalized. The only thing that matters is the Reynolds number. So as long as all your units are consistent, you can say my 1 unit represents 1 meter. Yeah, 1 meter. The velocity is 1 meter per second. And the nu is accordingly meter per second, meter squared per second. So that's why you take rho to be 1. That's fine. It doesn't mean the simulation is weird. The Reynolds number is the only thing that matters.
Okay.
Okay. Questions about the project?
No.
You can use finite volume if you like. Okay. So again, when you have questions about the project, just email me. All right. We were talking about the finite volume method, and just a quick recap on what we covered. So we said that we have to switch from our view of looking at discretization as point-based to cell-based. Okay? And we were doing this in 1D where we had node number I minus 1, we had cell phase, we had node number I plus 1, and here we store the scalar values. So we can say the average row of cell I is stored at the center. And all the cell faces get to store the velocity. So we will say u I plus half is stored here, and u I minus half is stored here. Okay. And then using the concept of control volume, we basically derive the conservation law, the conservation of mass, which looked something like this. We had a volume integral of rate of change of density, and when we take dV, this just becomes rate of change of mass. Okay. And there was a surface integral of rho u dot n ds or dA. And this was the flux of mass across the cell phase. And then, using divergence theorem, so Gauss's theorem, or it's also called divergence theorem, we can just simply say that this the surface integral is when written as a volume integral, it's nav plot dot rho u dv. Okay. And this is how we go from the integral form to the PDEs that we are so familiar with. So this means this whole thing becomes del rho by del t plus lambda dot rho u equals 0. So this is PDE for conservation of mass. And then we talked about, all right, so fine, we have this integral form. What do we do with it? How do we discretize this? What is finite volume? So finite volume turned out to be, we got a time change would be represented as rho bar. So this is average. I will write down n plus 1 minus rho bar at n divided by delta t plus what? Do you remember? What was it? So, you know, with a differential form, we would take finite differences, but that's the beauty of finite volume. You don't have to deal with the derivatives in space. You use the flux form. Do you remember what was here?
So flux east minus flux west.
Yeah, so flux east minus flux west. So east for us is I plus half. So I can take F I plus half minus flux I minus half divided by delta x. Delta x is the cell size, right? And flux is basically U I plus half rho I plus half. For flux. Okay, and then just also write rho bar is just the average rho. Yeah, rho bar is just the cell average, right? And you know, for a 3D cell, we would have the cell volume, but for the 1D cell, the volume is just delta x. Okay, for 2D cells, it will be delta x times delta y. Okay, so that's a very quick recall on what we were doing last time. Okay, now, how would, so this is fine for 1D. What would happen in 3D? What would we do?
Three different fluxes.
Okay, so
Delta x, delta y, delta z. From in a cell.
Yeah, in a three-dimensional cell, you have 6 faces.
6 faces.
In a 1D cell, you have 2 faces, face left and face right. It's not sort of a face. Right? So here we had only the x fluxes. Now we will have x, y, and z fluxes. Okay. So this it's very nice in that sense that it stays very consistent. So we'll get a similar term as this for y and for z. So let's see how that happens. So let's draw a 3D cell. So let's see. Okay, so here we talk about flux east. There we talk about flux west. And the cell center stores something. There's flux north. There's flux south. Okay, and there's also flux, let's call it forward and backward. Forward would be out of the paper, backward would be into the paper. So, okay, so what happens then? Where should we start? So the first term is d rho by dt. Fine.
It's the same.
Okay, it's the same, yes. So we have rho I, and we'll put a delta V over here. Minus rho I bar at n. Okay. So see, this discretization is just saying I am discretizing the first term, which is rho dV divided by delta t. So rho dV divided by delta t. Okay. All right. And we also talked about, all right, flux is rho u times a actually. In 1D, there's no a. So this is the flux, rho u a. All right. So let's start with east and west. What should I write? Let's say this is x, y, and z. Okay, east and west. What do we write? Right.
East minus west over delta x.
Where did the delta x come from?
From the west to the east.
No, so see, try to relate this term to this term. So delta x actually originated over there. Okay, so in 1D, delta v is actually delta x. Okay? And the surface integral has no delta x, it's just flux east minus flux west. Okay? So we will write a flux east minus flux west, and let's say the dA is out, so delta A. Surface area of the face we are looking at. What is the surface area?
Delta y, delta z.
Let's see, so you're saying it's a delta y and a delta z. Alright, so let's see, there's a delta y and delta z. Alright, what's the next term? Okay, go on. Yeah, take a guess.
The same flux.
The same?
North minus fx
Okay, so flux north minus flux.
minus delta y.
We're saying delta x times delta y because this is delta x and
This is delta z.
Delta z. Yeah.
alright, so delta x times delta z plus so there's the last two faces that remain, let's say forward and backward. Yeah, forward and backward. Flux forward minus flux backward. What then? Yeah, delta x, delta y, right? Equal 0. Okay, and that's it. That's the finite volume discretization of conservation of mass. Okay, and okay, now we can actually use what is delta v?
Delta x times delta y times
Delta x, delta y, delta z. Okay, and now you can see that when we divide throughout by delta v, we will have the same form as what we had here, but in 3D. It's very simple. So let me write it out and then which implies rho I bar n plus 1 minus rho n t plus flux east minus flux west over delta x plus flux north plus delta y flux forward minus flux backward delta z equals 0. So that's it. That's the, there's no assumptions here, no simplifications. Now, the biggest advantage of doing this is, does anybody know what's the biggest advantage of using finite volume methods? If we think about what happens when we look at cell number I minus 1, okay? So, what does flux do? What physical meaning? What is flux?
Is the flow rate over an area?
Yeah, it's mass flow rate, right? So it's how much mass is flowing this way, if we talk about mass. So flux out of I minus 1 is exactly equal to flux into cell I. Okay. So if you look at all of the cells starting from the very beginning, cell number 1, cell number 2, dot, 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 all the mass that leaves one cell goes directly into the other cell. So you are conserving mass perfectly. Okay? There is no sort of numerical error in conservation of mass. Does this make sense? So this is the biggest advantage of finite volume methods. Even with very low grid resolution, by construction, mass is conserved. Okay? That's just the property of the method. So let's just write that down. Let's see. So biggest advantage of finite volume methods inherently conserve mass exactly even for Does this make sense? So this is the most important property of finite volume methods. This is not true for most of other finite difference. You might start losing mass if your grid is too coarse. So that can be an issue. All right. Okay.
Sorry, for the finite difference, we had a similar concept, right? Meaning, why not in finite difference we don't have that conservation of mass inherently?
See, with finite difference, when we used pressure projection, we were enforcing continuity. Okay? But using pressure projection is not the same as finite difference. It's, finite difference is a method where you discretize derivatives using one term minus the other. Right? But here we are no longer talking about single grid nodes. We're talking about cells where there's stuff flowing in, stuff flowing out.
Because of, yes, okay, that volume. So
Yeah,
that's
it's
the
a
reason, right? The flow.
It's a lot.
So yeah, in finite difference, we are not dealing with cells or
Yeah, there's no fluxes across the cells. And talking about flux is the easiest in the case of conservation of mass. So the same thing applies for the diffusion term or the momentum equation. Okay? Any differential equation can be written in this form. It's called the conservation form. Okay, so yeah, if you remember one thing about finite volumes, remember they are inherently mass conservative. That's why most commercial software, they love to implement finite volumes. Inherently mass conservative, and you don't have to do complex grid transformations, complex equation transformations when you use non-rectangular grids, non-Cartesian grids. All right, so now this is conservation of mass. Now, if I say there's a source term in here, in this cell, which is pumping in some fluid. So, how would this equation change?
Plus Q.
Yeah, you can just add a source term on the right-hand side. Instead of being 0, it would be that source term in, again, flux form. Okay, so that's it. Right? And that we will see when we look at the momentum equation, because there we have pressure, we have viscosity, which are all sources of causing acceleration or deceleration. So they act as source terms. We can actually look at that right now. All right, so similarly, the momentum equation, the conservation of momentum, can be discretized using finite volume. Okay, and remember, there's always, we start with, there's a rate of change in time of what? What goes in here?
It can be rho, it can be
We're talking about the conservation of momentum.
momentum. Yes. Rho m.
Okay, so other guesses? Rho m, rho m, rho m.
Rho dv into velocity into u.
You want me to put a rho that I will agree with? What else?
V, the velocity.
Okay, what do we say? Alright, yeah, alright, so fine. See, it's, if you think about it, it's if velocity is constant, then this is rho dv is mass, du by dt. Okay, velocity is not constant. Du by dt is acceleration, mass times acceleration is force. Okay, so this is the most general expression for force. This is basically impulse, right? The term inside is impulse. I'm blanking on what the rho u is called. What is mu called?
Flux.
No, mu. P equal mv. What is P?
Momentum.
What?
Impulse,
Sorry.
impulse and momentum.
Yeah, no. So this change of momentum, right? Rate of change of momentum.
You're talking about vibration, two different.
Huh?
That term. Sorry, I'm coming.
No, okay.
This
So
is a similar thing. It's a similar thing for example, two different objects. They hit to each other. You know,
they
impulse
conserve-
and momentum. The
yeah,
momentum
they
is
conserve
conserved.
momentum. Yeah, so you can actually derive all of that simple stuff from here. Okay, these are basic laws, so the ones we are studying. Like solids, fluids, anything. Okay, so all right, we have rate of change of momentum, and that happens in time and also due to what?
Transfer of momentum.
Yeah, flux of momentum. So we have a rho u, which is a little weird, dot n dA. Okay, this flux of momentum across across the center face equal 0. 0 or not?
If there is no source, then it will be 0.
Right. So if you're in vacuum in space, fine, we can set this to 0.
Yeah, but if it is expanding, we can't. Expanding more.
Yeah, if anything is happening on the planet, we cannot set this to 0. There's two very important terms that accelerate or decelerate fluid, which are
Viscosity,
viscosity, decelerate fluid, and
losses,
Pressure gradient.
the pressure gradient, right? So there's pressure and viscosity. Together they form what's called the stress tensor. Okay, and then there's isotropic part is the pressure, and isotropic part is viscosity. Okay, so this will be equal to sources of acceleration. Sources of acceleration. Okay, and I'm not going to write the nabla p over rho directly. You will actually derive where it comes from. Right, okay. So, by the way, this is the term we change into nabla dot rho u dv, and we use Gauss's theorem. Okay, so source of acceleration, let's see. Two main sources of acceleration in fluids. Okay, there's pressure and there's viscosity. Okay, so when we talk about pressure, what happens? If I say there's a wall over here and I have some fluid over here, I know the pressure at this point. What will be the force acting on the wall?
It will be P over A.
P over A?
Surface.
P divided by A?
P times A, sorry.
Okay.
Yeah.
P times A, yeah. And we're talking about force, which is a vector.
Yes, and there will be a normal length.
All right, so let's see. Surface normal is this thing, right? So give me the exact formula. So F pressure is what? Let's say I give you, there's an infinitesimal area, right? dA. Okay, F pressure is equal to
P times dA.
integral.
what's more?
P times dA times N.
P, yeah, N dA, right? Plus or minus?
Minus,
Okay, explain why.
because it must be orthogonal to the surface, so it's not positive, it's negative.
Yeah, so the normal always comes out of the surface,
Yeah.
but the pressure force will be acting towards the surface. So that's why minus N. Okay, and that's dP, so that's an infinitesimal force. And we just integrate it over the whole area. That becomes force net. Okay. So we have the surface integral for pressure at finite volume once. Okay, well, let's actually in terms of a volume integral, what is this? This can be written as what can this period mass?
Gradient of
What sort?
grad P.
Alright, now P.
Yeah, volume integral
Volume integral
and dV.
dV. And this is the term we are very familiar with. Of course, I missed a minus. This minus goes here. So this is minus nabla P over rho that we keep writing on the right hand side. Okay, so we have one of the terms on the right hand side. Well, let's go look at the second term. Okay. Now for the viscous term. Okay, where do we start? Okay, let's start with the wall. Right? We have a wall, we have the normal, then what? Friction, okay, but how?
Shear stress.
Alright, so what's a very simple formula for shear stress that you know? So F shear is equal to
Tau.
Would be mu del U by del Y. So
yeah, mu del U by del Y, right? This is for a flat plate where you have a nice velocity profile, right? You compute the gradient of U with respect to Y, multiply with the friction coefficient, the viscous coefficient, and that's the force. And of course, there's a dA over here, right? Make sense? All right. Now, this is valid for a very special case where we have a flat wall and it's aligned with the x direction, etc., etc. What's the general formula?
there would be del V by del X as well. And,
Yeah, there would be del U by del x and many terms in there. So somebody mentioned tau.
Yes, your mu del U del Y is tau. Is tau shear stress.
That's tau in this very special case. Do you know the general formula for tau?
we can write a tensor tau ij.
Tau I.
Yeah, so in general, in 3D, we use the tau tensor. Okay. So in 3D, F viscous is tau tensor dot n dA. Okay, and we can integrate this over the surface. This is the anisotropic part of the stress tensor. What is the other name for this? Shear stress. Right. Yeah, shear stress. This is the shear stress tensor. Okay, and tau is actually, do you know what tau is? Yeah, we've gone very deep into very basic fluid mechanics. So, what is tau? Somebody was talking about velocity gradients.
There would be so many terms, Kronecker delta and
Yeah, the simplest expression is 2 mu d I d. Right? And this is the strain rate tensor. Strain rate tensor.
yeah.
And this is equal to half nabla u plus nabla u transpose. Okay? So all of the complex u by dx, dv by dy, etc. You know, this is it. Okay? There's nothing more. No simplifications, no assumptions. Okay, so we have tau equal to mu times this whole thing. Alright? So what we get is F viscous is integral of mu. Let's take mu out. Mu is a constant. Mu mu what? Mu r. All right. Nabla u plus nabla u transpose dot n d a. These are tensors. Tensors dotted with n will give you vectors. Force is a vector. Always do these checks in your head. Everything should make sense. Okay? So now we have the full Navier-Stokes in the integral form. So let's see. So we have, let's see, on the left side we have d rho u. I'm just rewriting the left hand side. dt dv plus flux of u equal the first term, this term, minus p n dA plus the viscous term, mu nabla u plus nabla u transpose dot n dA. Okay, and do you see now how you go from here to the PBE we have been talking about for months? Who sees that?
Yeah, it's all integral, so we can simply convert them into the volume integral first.
Okay, so let's use Gauss's theorem to convert all surface integrals. By the way, for finite volume, this is all you need, right? So you have everything in the surface integral form, which gives you the fluxes. Okay? And we will look at in each term how we get the viscous flux and the pressure. Okay? Convert all surface integrals to volume integrals. Okay, so what we get is basically, alright, the first term stays del by dt rho u e. Second term becomes, what does it become?
Rho u dot L.
Nabla dot rho u u, right?
Nabla.
Yeah.
dv blah equals
Nabla p.
Nabla p.
Nabla square u.
something weird happened here, right? So there's a nabla dot nabla u transpose. When you take nabla dot on both these terms, you just write them as nabla dot the first term, nabla dot the second term. Okay? Alright, so we're almost there. So let's see. Do you know how to simplify this?
Should be Nabla square, right?
Both the terms go to nabla squared u?
No, it's first time Nabla square u. First
Okay.
time Nabla square u transfer.
This term is actually 0. Do you know why? Let's see. So, okay, first let's expand this guy, alright? Expanding this guy, we get nabla you get u dot nabla rho u plus rho u nabla dot u. Okay? When you expand this, you get these two terms. This is 0 continuity. And this is what we du by dt plus u dot lambda u equal blah blah blah. Okay, so let's see. Left hand side becomes triple integral of, let's say a rho is constant, so we take rho out. Del u by del t plus u dot lambda u dv. Okay, and you recognize the part-hand side, left-hand side of Navier-Stokes. Okay, so let's see. Let's look at these two. Well, let's look at the interesting one, which is lambda dot lambda u transpose. Okay, so let's stick with 2D. 2D means we do, what do we do? What is this? How do I write this term in 2D?
Del by del x and del by del y would be the column vector, and there would be u and v in another row vector.
Then?
And u would be in the another vector, u, the velocity vector. Oh, it's all already there.
So we transpose this, right? So this is lambda u. Right? Then dot with lambda. How do we do that?
Del by del x, del by del y. Yes.
How? How do I arrange this? You're right. D by dx and d by dy. Just multiply with the column vector.
Yes, column vector.
So we have d by dx and d by dy. So this is lambda dot term, lambda u transpose is over here. Okay, so let's see, what does this mean? Okay, yeah, I should write up one more step. So du by dx and dv by dx, du by dy, dv by dy. D by dx, d by dy. Okay, which is equal to dx squared. So this is not 0. Why did I say this is 0? Is this 0?
Yes, if you.
Yeah, I will wait.
We're talking about this term. This term, I agree with you, becomes lambda squared u. Okay, you can do it later. This term is 0.
Continuity can be put in
How do you use continuity here?
there. Del by del x,
del
del u
by
by
del
del
x.
x plus del v by del y.
Okay, so we take one of the partials in x out, and what we get inside is dv by dy. The other one the same. Okay, and the stuff inside is just lambda dot u, 0. So make sense? Okay. we basically have recovered our momentum equation. Left-hand side, you will read, this thing becomes this, and the right-hand side becomes triple integral of minus nabla p plus mu nabla squared u dp. Okay, and yeah, the two terms inside are just the two terms we get. The rho will here will come down, so we get an nabla p over rho, and mu becomes nu. Okay, but that's it. So everything is related in one way or another. Okay, so fine. Now that we are convinced the momentum equation also works, what would I do for finite volume discretization of this equation? Okay, so let's see. Finite volume discretization of momentum equation. And again, let's always draw our cells because that helps us keep track of what goes where. So rho I would go here, u east would go here, u west would go here. And let's do this in 1D. Okay, so let's use this equation we wrote here, and you tell me one by one, what does this term become? This one. No. For observational mass, we had a rho inside. Now we have a rho u inside. What did the first term become in observational mass?
Del rho over t. Partial rho. Partial.
Yeah, but in finite volume terms. That's the first term, right?
The first.
So we can do something similar.
Yes.
Okay, so what do you want me to do with this?
You can use rho u.
Rho u instead of rho u.
Yeah, exactly. So the first term becomes the rho u bar at I n plus 1 minus rho u bar at n I over delta t. So that's another thing in finite volume. You keep track of several different variables. So rho u is stored as one variable. Okay.
Can't we take rho out?
No, you should not, because that's the point of doing this in conservation form. Yes. Okay. Okay, so you can take rho out only if it's constant. Okay, but in general, this is how you would discretize it. So yeah, this makes sense, right? What's inside, we store as this. Okay, fine. What does the flux term become?
Divergence theorem.
With finite volume, remember, we want it to stay
Flux.
in flux terms. Right? So what's the next term? How do we discretize this?
FU is that?
Flux u?
Flux u.
Flux u is rho u times u, right? So we can write, okay, flux u, flux east
Flux
minus flux west over delta x, right? equals something. So again, this is a very general form, valid for finite volume in general. You just have to figure out what the flux is for the equation you're dealing with. So for the momentum equation, the flux east is basically rho u east times u east. Okay. And this will be rho u west times u west. Does this make sense? So in the very general finite volume code, you would store rho u and you would store u. Okay. All right, so this is the full left-hand side. First term, second term. First term, second term. Let's look at what goes on the right-hand side. Okay, so right-hand side becomes, this is the shares. Okay, first term on the right-hand side is this. What should we do with this?
This would be a line integral only.
So again,
Yeah, true. So in general, it's a surface integral dA. Now it will be a line integral.
Yeah.
And we assume span out of the plane is 1. So, so fine, but in discretized form, how can we write this? Think again, always in terms of east and west. Whenever there's flux, you have to go east-west, no cell centers.
Yeah, so P A east minus P A west.
Yeah, so it's P east minus P west over delta x. And there's a minus term here.
so
You said A. A would just be L.
Yeah.
And which is 1. Right? And the delta x comes from, there was originally a delta V here, which becomes a
Yeah.
delta x in 1.
But for the general case, there would be A, right? Yeah, but in this case, it's
In general case, there would be an A divided by delta V, which would give you delta x. So this would still be valid. It's the same thing we did in 3D. Remember this we did in full 3D. There was an A divided by V became delta x, delta y.
But when we deal with some complicated geometries, this won't simplify to this.
No, yeah, of course. Then you have to have an A divided by delta. It's only with very nice cuboids or quadrilaterals. No, what is it called? Rectangular boxes that this becomes this simple.
trapezoidal.
Trapezoid? No, not trapezoid. And box-like cells, this becomes nice. Okay, so that's first. Let's see. What's the next term? Next term is over here. Oh, what should we write? Always go back to thinking about fluxes. When we had the surface integral, the flux was the thing inside the brackets. When we have surface integral, the flux is the thing inside the brackets. That's it. So we will write plus flux, let's say mu of east minus flux mu of west divided by delta x. And here, flux mu east is basically mu times nabla u in 1D, right? So it's basically du by dx. East. And there's no dv by dx. So yeah, that's it. Du by dx. Du by
Why?
dx.
Or it should be other direction. friction is normal to the viscous.
What did I do? I know this is correct. So see, du by dx divided by del x will become del 2u over del x squared, which is Laplace squared u.
Sorry, what is this flux? The flux. This is
This is the viscous flux.
viscous flux.
Yeah.
So this viscous flux in the x direction.
Huh? Okay. So do you agree with this part? Right hand side is
Yes.
mu Laplace squared u.
Yes.
In 1D, what will this become?
East minus west.
No, 1D in partial differential equation. This is just d2u by dx squared. Laplace squared u, how do you write this? d2u over dx squared plus d2u dy squared plus d2u over dz squared. That's the x component, right? And in 1D, only the first term remains. Okay, wait. So let me just write this. Laplace squared u, how do you write this? Del 2u over del x squared plus del 2u over del y squared del 2u over del z squared. This is the ith component. Plus del 2b over del x squared, blah, blah, blah. Does this make sense now? So this is the x component, and in 1D only one part remains, which is what this flux will become. And you have flux east minus flux west. It's like taking the derivative of the derivative, which is the second derivative. Does this make sense?
Yes.
Alright, so let's. Okay, so yeah, that's basically it. On the left hand side, we have these two terms, and the right hand side, we have these two terms in 1D. That's all there is for finite volume discretization of the momentum equation. In 3D, you would add more fluxes, north, south, forward, and backward. That's the only change.
Grad U transpose would become 0 here as
Yeah. So this nabla dot nabla U transpose was we derived for the very general case, right? It's in any dimension this is 0. So here too it will be 0.
But we didn't take it like right now. We were dealing with a surface integral, not the volume integral, in writing this. So we were just dealing with grad U.
Oh, I see. So nabla U transpose in one dimension. How would you? I don't even know how to write that for a 1D case. In 2D, you take the matrix and transpose it. So this term would be the
Yeah,
C
this both would be
dv
used.
by dv by dx,
Mm.
right? Which is 0.
So, yeah.
Does it make sense to you? Okay, so now if you want to code this up, you can actually do, and it would be the finite volume method. Okay. Any questions for now? All right, so let's talk about this diffusive flux a little more, okay? And let's take a simpler equation. So let's take the pure diffusion equation. Pure diffusion equation for a passive scalar is what? Passive scalar, let's call it phi, alright? So what is the partial differential equation?
Del square phi by del x square. Del phi by del t equals to grad square phi.
There's a kappa here,
Yeah, kappa.
diffusion, right? And this is basically in 1D it's kappa del 2 phi over del x squared. Okay, and now let's do this in finite volume. Like so integral form would be would be what? This is the differential form. What would the integral form look like? The time derivative. Volume integral or surface integral?
Volume.
Alright, so let's do a volume integral del phi by del t. So right now the form is this minus kappa lambda squared phi dv equals 0. Perfect. So let's keep the volume integral on the first term. dv. What happens to the second term? We want to change it to the surface integral. What does lambda squared phi dv change it to? Right, so-
Simply that.
Yeah,
Now,
lambda phi, then?
Dot n hat.
Alright, dot n hat, ds, dA. Right, that's it. Because lambda squared phi is lambda dot lambda phi, and then we go from volume distance. Alright, so discretize this in finite volume form.
Similarly,
5 bar
Phi bar,
at phi
I,
n plus 1
n plus 1,
minus phi I n over delta t
and we put a delta v in front,
delta v.
right? Because phi bar is the average, and we want the total in the volume, in the cell. Okay, and then what?
Minus kappa f east minus f west. No, that's over delta x.
No, no delta.
the delta in delta
Okay, and there would be north and south, that's it. Okay, and now we get the delta x you were talking about. How?
By divide.
Delta A divided by delta V is delta x. Okay. What is FE?
That is phi times a.
No, A is over here.
What is a?
Okay, FE is what?
grad phi at east.
Yeah, it's just the thing inside, right? The thing inside the brackets here. So it's nabla phi east, and this is nabla phi west. Okay? And again, let's do this in 1D. It becomes very, very clear. So 1D, we have something over here, something over here, I plus 1. We have a cell face, okay? And we have a cell face here, east, west. And we have an I minus 1, and here we store phi above I. Okay. So, okay, so I'm just rewriting phi bar I n plus 1 minus phi bar n I over delta t minus kappa nabla phi east minus nabla phi west over delta x equals 0. Okay, now we need to figure out what nabla phi east, nabla phi west are. But remember, the only thing we store in finite volume schemes is the cell average. Phi bar I plus 1, phi bar I minus 1. Tell me one way you would like to write nabla phi east.
Be phi I plus 1 minus phi I by.
Okay, so find one possibility of one candidate for nabla phi east is Sorry?
Phi I plus 1 minus phi I bar
Bar.
and divided by delta x.
Okay, so, he didn't do much. He just said, okay, I will assume there's linear variation between the cells. So this minus this divided by delta x give me the slope, which is what we wanted, slope on east. Similarly, slope on west is
Yeah, phi I minus phi I minus 1.
and when I write delta x, I'm assuming all the cells are uniformly sized.
Yeah.
If that's not the case, you cannot write delta x. You can write xi plus 1 minus xi. Okay, and when we put this in here, what happens? Let's see. Which implies phi I n plus 1 minus phi I n divided by delta t minus, let's take it to the other side, kappa. Okay, what do I get? I get phi, what do I get inside?
2 phi I n or phi I plus 1 minus 2 plus phi I minus 1.
Yeah, so I'm just substituting these two into this term. And we get what?
Delta x square.
Does this look familiar?
Yeah. Central difference.
Yes, central difference.
Yeah, this is the center difference formula for the second derivative. See, everything is consistent, everything is related. Even though we are in finite volume, we are not completely isolated from the finite difference world. All right. So, any questions for now?
So it's interesting. What is the connection? Can we connect that finite difference and finite volume? Something from this last equation? Is there any?
No, they're okay. So the methods are, they're not completely Earth and Mars. They are methods to discretize the PDE, the governing laws. One of them just stores actual values, finite difference. The other one stores cell averages, finite volume. And the way you would implement this in the computer would also be different because here you store everything at the cell. Here you have to have two different indices, one going through the cell centers, the other going through the cell faces. And yeah, so programming becomes a little more important. Also, the finite volume conserves things exactly. Finite difference. At high gauge resolutions, you're good. Okay. All right. So let's see. I was going to talk about advection. Let me see if I have enough time. I have 12 minutes. Yeah, we can start talking about advection. All right. So this was pure diffusion. Okay. So let's see. Let's look at pure advection now. Pure advection. Again, for a passive scalar. What is the equation? Passive scalar is phi. What is the equation?
Del phi by del x u dot grad phi.
Okay, this is the derivative form, right? Can I change this to the conservation form? This is the non-conservation form. Conservation form meaning talking about fluxes. Flux is quantity times u. That's the flux. So I want to change this term so I get something that looks like a flux. We're going in reverse. So we're going from the PDE to the integral form. The proper way to do this is start from integral form, go to the PDE. Just so you'll see how exactly these two are related. We'll go in reverse.
Can be written as del dot phi.
This can be written as what?
Del dot grad dot phi
Laplace Volume.
divergence of phi u phi.
Does everybody agree?
Because if we can consider continuity here.
Okay, so if we expand this, what happens? Nabla phi dot u plus u dot phi nabla dot u, right? So we basically added a 0 over here, which means this is a 0. So this is equivalent to this, or incompressible. So again, we have the volume integral del phi by del t plus nabla dot phi u dv equals 0. What should I do?
Same thing.
Okay, so
Phi.
dictate and I will write. No?
Yeah, phi I.
Let's write the integral first, right? So
Integral dou phi by dou t dv plus volume integral of
we're trying to go to the surface integral. Okay, so
surface integral of phi u dv. Sorry, n cap dv.
good. All right, this is in finite volume.
Phi I n plus 1.
So phi,
Minus
yes,
phi.
phi I or n plus 1.
Plus flux east
Flux.
minus flux west.
East minus west. So F
Inverted legs, yeah.
F is phi u.
Is what?
Phi u.
East and phi west.
Okay.
So is it possible to write every expression which we want to solve in conservation form? Because if it's not possible, then it would be difficult to do this.
Yeah, if you cannot write it in terms of fluxes, how would you?
Will we integrate the whole thing numerically then?
Can you integrate the whole thing? What?
I mean, in that case, will we be integrating the whole thing numerically?
I don't know how you'd represent that in finite volume form if you cannot write it in conservation form. I can find out. So let me check, and I can tell you next class. We only have next 6 minutes. Yeah. So well, at this point you should be very comfortable jumping from the PDE form to the integral form, changing to surface integrals, and how that goes to the finite volume form. And this can be done for advection equation, diffusion equation, advection diffusion equation, momentum equation, anything. Okay. Luckily, most conservation laws we deal with come from conservation form because this is their the basic law, right? This is how they're derived. This is, we come here by manipulating slowly. So yeah, luckily most of our equations are already in this form. Okay, makes sense? Okay, so let's stop there for today. And again, please start early on the project. It will take you time. I told you it took me 6 hours. I'm a little ashamed of that, but fine. So yeah, and when you're stuck, just email me. We can talk over Skype. Okay. All right, so let's go.
Why are you so happy? No, I missed my shoes.
I thought you were happy because of finite volume.
So one more question, like do these methods, the finite volume, previous case really with grid
After we
convergence?
Yeah,
I don't know. I have never done a grid conversion for a finite volume.
Hmm?
The only time I coded a finite volume method was when we were using hyperbolic systems for an actual research code. I have never done it. I don't know. I would have to find out.
I read it
Because
for
like, intuitively it should be
presentation.
Yeah, it's
like,
exactly
bad. I mean,
bad because everything looks no. So it depends on the interpolation. So
Next week.
we assumed phi east is
Yeah.
average of the right. So there the order of accuracy comes in.
yeah, true.
No, I will present you guys.
Oh.
Great. So we will take apart the stuff after I eat. Please.
No, because if we wait for everyone's lunch, you will find no one there.
Meet me there at 1 p.m. Better?
I'll check my schedule.
Okay. And yeah.
By the way, I have no limitations with the places you're sending me through.
Once more?
I have no limitations with the places you're sending me through.
With the places.
The conferences and their locations.
Oh, no, I don't want to.
Just
make you
please don't
travel
send me
to
to Alaska or Oceania. I would prefer coming back.
Do I have to move the systems?
Oh yeah. So Sumit and Aishwarya, can you shut down your systems and move it to offices wherever
Sure.
Fiona tells you to? I think she already has picked up.
Okay. Yeah, we can say. Like, can we sit on Friday
Friday?
meeting time, like after meeting?
Our meeting is on Friday or?
Yeah.
This week is on Friday, not Wednesday.
Then we can sit down.
Okay.
Or like you can tell me some other time whenever you are free. You're not
Yeah.
free that day.
Oh, Friday is good, or today or Friday.
Today is a bit
Yeah,
tight
you
for
wanna-
me. Like we will be disassembling something and things, and then like I will go early because I have some assignment deadlines.
Oh,
I usually complete the assignments on deadlines.
have you started the project, the final project?
Not yet.
Neither, but I want to work on it. I think the last project is
It's
good. It's
and it gives you. It feels good when you make good animations. That feels good.